Welcome back, Virtual Physical Science. Section 7.2 is all about electrical current. And we can contrast static electricity, the kind of electricity that we looked at in the other situation where the balloon and the hair held electrical charges and attracted each other. That's static electricity, and we're going to now learn about current electricity. Static means not moving. That's what the word static means. And static electricity is meant to refer to situations where electrical charges are there, but they're not moving. So, like on the balloon and on the hair, they could attract each other because one was positive and the other was negative, but they weren't flowing most of the time between one object and another. So we call that static electricity. In current electricity, the charge carriers, most often the electrons, are moving through something, a wire or a person or whatever. Alright, well why would charges move like that? Your book uses an analogy with water flowing through a system, and I like to use an analogy with gravity pulling something down a hill. If we put a ball on a hill, it's going to roll down, and we'll watch gravitational potential energy turn into kinetic energy. Well, what we can do is kind of make an electrical hill, and we use something called voltage. Okay, if something has a high voltage and then a low voltage in another place, an electrical current will flow down that voltage hill. It will flow from high voltage to low voltage. And what we're seeing there is an expression of electrical potential energy. So keep this analogy in mind between something falling down a hill and a current moving from high voltage to low voltage. All right, an object is always going to roll from a high part to a low part on a hill, and electrical current is always going to flow from a high voltage toward a low voltage, from positive toward negative. Okay, and a voltage itself is measured in volts, and it's named after a scientist, Mr. Volta, who studied electricity a long time ago, invented some of the first batteries, and sometimes the symbol for volts is just abbreviated to V. And it measures the electrical potential energy of something. Okay, so voltage is actually a measure of that electrical potential energy. And how much current, how much electricity flows through something is going to depend not just on the voltage, but on the voltage difference between the two ends. Okay, just like in this situation here, this ball is still going to roll down this hill, but not very fast, even though the left side of the hill is really high up. Because the right side of the hill is also really high up, the ball just is not going to roll very fast. Okay, and so in that situation, it's not necessarily how high the thing is that the ball is rolling on that matters. It's the difference in height between the left side and the right side. Okay, if the right side was much lower, the ball would roll much faster. In the case of electricity, you can have two places with the same high positive voltage, but if they have the same high positive voltage, no current will flow between them. Okay, what you need is a place with high voltage and a place with low voltage. Just like in the hill, you need a top of the hill and a bottom of the hill in order to make the ball roll. With current, you need a high voltage and a low voltage to make electrical current flow. Current itself is measured in amperes, often abbreviated as amps or even A. And for some reason, in equations, it's given the symbol I, which is annoying. Voltage measured in volts, current measured in amperes. Ampere is also a famous scientist who studied electricity, a Frenchman. Okay, so how do we create this electrical hill? Well, batteries are a great way to do that. A battery maintains a voltage difference between two places. A 9-volt battery can guarantee you that the difference between the positive and negative terminals will be 9 volts. And so it is essentially an electrical hill. Now, when a ball rolls down a hill, kinetic energy is a little bit of the kinetic energy is lost to thermal energy, because as the ball rolls, the hill and the ball heat up a little bit. Why? Well, there's friction in there, right? As those surfaces rub against each other, some energy is going to be lost to thermal energy because of friction. And the same thing is true in the case of electrons flowing through a wire, in the case of electrical current. What happens in an electrical current You see this wire, there's a positive charge on the left, high voltage, and a negative charge on the right, low voltage. So which way is the current going to flow? Right, the current's going to flow to the right. Unfortunately, current is defined in a wacky way, and electrons are actually going to flow the other direction. Which makes sense. They're going to be attracted to the positive charge. Anyway, that doesn't really matter that much. What matters is that you look at this picture and you imagine the electrons moving, these negative red guys, moving to the left, and they're going to bang into all the atoms, these black dots, and they're going to bang into each other. It's crowded in there, and when they try to get through this wire, they're going to smash into things. And every time they smash into something, they heat up a little bit, and they lose a little bit of their electrical potential energy to thermal energy. The good thing about conductors is that this resistance, this electrical resistance, which is like electrical friction, is low. In insulators, the electrical resistance is very high. Electrical resistance gets the symbol R in equations, which is very sensible, but the units for it are funny. They're named ohms, and they get this crazy omega symbol. All right, and that's also another gentleman who studied electricity a long time ago, Mr. Ohm. But electrical resistance depends on lots of different things. Firstly, it depends on temperature. Pretty much everything becomes a better conductor if you cool it down. If you cool down a metal to a lower temperature, it's going to have a lower resistance. But even if you cool down an insulator, it's going to have a lower resistance. Okay, imagine that this electron is going into a crowded room, and he wants to get to the other side. Maybe he sees a girl on the other side of the room, and he wants to go talk to her. Well, he can pretty easily work his way around these people because they're not bouncing around too much. But if the music starts and all the guests in the party start dancing, then maybe the situation looks more like this. Well, in that case, because everybody's moving around, the electron's going to have a lot harder time getting to the other side of the room. And that situation corresponds to a higher temperature. Remember that temperature measures the motion of particles inside something. So a higher temperature means that the particles inside the material are bouncing around and moving around faster, and any electron that wants to pass through is going to have more resistance. It turns out that if you cool some particular materials down to very, very, very cold temperatures, they become what's called superconductors. And they acquire the property that they have absolutely no electrical resistance at all. And one thing scientists these days are trying to do is figure out a way to make that happen at slightly warmer temperatures so we can use that to make our electrical devices more efficient. But resistance also depends on the length of something. And this makes sense. If you imagine that electron trying to move through the room on the left, it's not very long, and so he'll have less resistance. If he tries to move through the significantly longer room on the right, he's going to have more things to get around and more obstacles in his way, so he's going to have a higher resistance. So longer things have a higher resistance. Resistance also depends on the width of something in kind of a surprising way. Wider things have less resistance. If the electron's going through this narrow room here, it's kind of hard to get around everybody because there's not a lot of places to go. But in a wider room, in a wider conductor, there are more paths to choose from, and so it's easier to get through. So wider things tend to have lower resistance. Okay, so those are three factors that resistance depends on. Temperature, higher resistance when it's hotter. Length, higher resistance when it's longer. And width, higher resistance when it's narrower. Mr. Ohm is so important that there's a law named after him. He figured out how current, voltage, and resistance all relate. And that's called Ohm's law. Current, represented by I, is voltage divided by resistance. We can rewrite that as V equals IR. And we can represent it by this circle thingy here. So let's say we plug our 100 ohm vacuum cleaner, has a resistance of 100 ohms, into the wall with 220 volts coming out of the wall. What kind of current can we expect? Well, you can see here and here that we divide 220 volts by 100 ohms to get 2.2 amps. So this math isn't too hard. Alright, it's your turn. Read up on current electricity, section 7.2, and when you get to page 207, answer all 7 questions. Good luck, guys. See you next week.